Let's look at a problem here where our vessel is turning, and we need to calculate the angle and direction of heel when turning, in this instance, to port. And we need to calculate the angle and direction of heel. Well, the direction is always opposite to which way you're turning. So we're turning to port in this problem, so the direction is going to be starboard. If we just look at a sort of simple sketch here, if you like. This is looking at a vessel from astern, and this vessel is turning to port. So she's hard over, say, turning to port, but she's actually heeling over to starboard. And the two forces you have acting upon the vessel, you have what we call a centripetal force or centre seeking force, and then you also have what we call a centrifugal force, which is a centre fleeing force. Okay, so centripetal is centre seeking, centrifugal is centre fleeing. Now, really, strictly speaking, there isn't any such thing as a centrifugal force. We do put that down and it's perfectly acceptable, but really it's all to do with inertia. It's all to do with inertia, really. You definitely have this centre seeking force, but it's inertia that is really involved with the centrifugal force, which don't want to go into it too deeply here, but just understand that when you're turning to port, you're going to be heeled over to starboard. If you were to have, say, something on the end of a string that you were swinging around, so you were swinging that round in a circle, you'd have a centre seeking force, a centre fleeing force. Well, the centre fleeing force is actually inertia, because if you were to suddenly let go of this, so here's you at the centre swinging it round, you to let go of it, if there was a centre seeking force and it suddenly went, it should just shoot off that way, but of course what it does, it shoots off that way. So it's to do with inertia, why you have this these two things acting upon the vessel. But if you were to have to describe this in an exam, it's perfectly acceptable to refer to it as centrifugal force, centre seeking, and centripetal force, centre seeking, centre fleeing and centre seeking. Okay, so let's look at the calculation. As always with stability, if you're unsure, go to your formula sheet. I strongly advise, you must look at the formula sheet when you're doing your revision as much as anything else and recognise the formulas to use. Tan theta, v squared times bg, g times r times gm. bg is the difference between kb and kg. G is 9.81 meters per second. R is the radius, that's the gm, and v of course is the speed. So we're given all our different values here, and let's have a look how we would calculate them all. Well, v squared, we have to get the speed of the vessel, 17.2 knots, multiply it by 1852 to convert it to meters, and then divide it by 60 squared, and that takes it to meters per second. Because our speed is per hour, we have to divide it by 60 squared to get it to seconds. So 8.85 meters per second. Okay, so that's where we get the 8.85 from. 3.73 is km minus, gm is km minus kg, 0.45, and bg is kg minus km. So bg, that's where we get that from. GM, of course, there, straightforward. And just be careful, often in these problems you're given a diameter, the circle. Well, you have to use the radius of a circle there, so we halve the diameter, 245. So we put those into the formula, and we got an angle of heel of 15.1 degrees to starboard. Okay, so that's how we solve that problem. It's a pretty straightforward question, nice question to get as long as you know which formula to use. The draft when heel, just use your normal formula. The upright draft times cos theta, which is the angle, 15.1, plus half the beam times sine of theta, 15.1 again. So draft when heeled is pretty straightforward, 10.6 there. and the angle of heel, don't forget it's to starboard if you're turning to port.